Welcome everyone to Chapter 5 in our course on approximation and stability. Chapter 5 is the last chapter, and this is about spectra, eigenvalues, so-called pseudo-spectra, properties that spectra have, and what's the deal with this little fish over there with the skinny bones. So yeah, stay focused and have fun. So let's start with section 5.1, properties of the spectrum. And let's get the little fish over here, maybe. Okay. So in this section, we always look at bounded linear operators A from X into the same space X. And for the moment, it's enough if X is a Banach space. At some point, we will need Hilbert spaces, but for the moment, Banach space is fine. Recall that a complex number lambda is called eigenvalue of A if A minus lambda I is not injective. Okay, so this must mean that the kernel has non-zero elements, and these are exactly the elements that we call eigenvectors. And if you spell that homogeneous equation out, it says that Ax equals lambda x, and that's exactly what you learn in linear algebra as the definition of an eigenvalue eigenvector pair. Now in contrast, lambda is a spectral value of A if A minus lambda I is not invertible. We spoke about the difference between eigenvalues and spectral values in chapter 1 already, so we can keep this short now. So if an operator is not injective, it clearly cannot be invertible. So if you're an eigenvalue, then you're certainly a spectral value, but in general not vice versa. So the set of all spectral values of A is in general a superset of the set of all eigenvalues, and we denote it by the spectrum of A. So let's also say this here. And something that we also mentioned already before is that when X is finite dimensional, let's say dimension is n, then A can be identified with an n by n matrix because it's X to X. And then injectivity and invertibility are equivalent because injectivity means every column of your matrix has a pivot after elimination, and invertibility means this and every row has a pivot. But if you have finitely many rows and columns and that's in the same number, then the two things are equivalent. So in finite dimension, eigenvalue and spectral value is just the same. So let's look at some examples. We're going to take a bit of time before we can do examples that produce this kind of spectrum, but not very long. Okay, first some simpler examples. Our first example is the backward shift on little lp. So it takes a one-sided infinite sequence or vector and moves everything one position back. So in particular, the first piece of data is lost. Okay, and the rest moves one position to the left. Now, because we don't quite know how to compute spectral values and the whole spectrum, let's start with eigenvalues. So we start with a good old Ax equals lambda x. And this is your x. So that's your Ax. And let me write it as a column vector because that makes it easier for us to compare the two vectors. Okay, now lambda x is just lambda times this vector. So we simply conclude that x2 is just lambda times x1, and x3 is lambda times x2, which then must be lambda squared times x1, and x4 is lambda times x3, which must be lambda power 3 x1, and so on. So our eigenvector x would have to look like this. So you can all roll it back to your initial value x1, and because that's just a number, you can just get it out as a factor. And before you can call x an eigenvector and lambda an eigenvalue, you have to make sure this is actually an element of your space LP. And this condition will give you conditions on the location of lambda in the complex plane. So for example, if p equals infinity, then you just want your vector to be a bounded vector. So you have to make sure that the powers of lambda remain bounded, and that's the case if and only if the modulus of lambda is less than or equal to 1. So geometrically speaking, that is the closed unit disk. So it's containing the unit circle, the boundary of the disk. And now let's look at some other values of p here. Let's say p equals 1. So our vector here is in L1. If and only if you can take the modulus of every entry, add it all up, and still get something finite. But now instead of modulus of lambda power k, we can also say modulus lambda and then power k. But that's just a geometric series, and we all know what sum is. Okay, so for the convergence of this series, we need that the modulus of lambda is strictly less than 1. And if it would be 1 or bigger, then it's clear that this vector is not a null sequence. It's if the modulus equals 1, then that modulus vector here would just be constant to 1. So it's an L infinity, but not an L1. And if the modulus is bigger than 1, then it's even growing, so not a null sequence. So this time we get the unit disk, but without the boundary. Okay, so think about what happens when p is somewhere between 1 and infinity, and maybe we can discuss this in the exercise session. Next example. So this time let's take the forward shift on LP. So you take your one-sided infinite vector and move it one position to the right. And in particular, you fill the empty slot here by a 0. Okay, let's again try and compute the eigenvalues. So let's write down ax equals lambda x, and ax is just this vector, and again we write it as a column. And again, lambda x is just lambda times this input vector here. And let's proceed like we did before. Well, the first thing we see is that lambda times x1 seems to be 0. Well, if a product of two numbers is 0, then one of these has to be 0. In the first case, if lambda is 0, then this whole vector on the right here would be 0, which means everything on the left would have to be 0, but that includes all entries x1, x2, and so on, which means that your whole input vector x is the 0 vector. But that doesn't count as an eigenvector. It would be just too simple, so we're not allowing this case here. So we have to follow the other road here. Okay, if x1 is 0, then let's continue with our next equation here. So now we have that lambda times x2 is 0, and again one of the two factors has to be 0. And we have already learned that it can't be lambda, so this one is not the one that's 0, so it must be the other one. So x2 is 0. But then going down here, our third component must be 0. So lambda times x3 is 0. Can you see what's happening? Well, we now get that also x3 is 0 and so on. So we have x1 is 0 and x2 is 0 and x3 is 0, and in that style you will continue to see that your whole input vector is the 0 vector. But like we said, that doesn't count as an eigenvector. So what's happening here? Did we do something wrong? I mean, we came up with this operator here and we wrote down what it means for x to be an eigenvector and lambda to be an eigenvalue. We computed these two vectors, we compared them component by component, and we ran into trouble constantly, everywhere. And we tried everything. What does it mean? Well, it means this operator does not have any eigenvalues and therefore no eigenvectors. And of course, it feels a bit strange to say that or to write that down because we didn't see that before. I mean, from your linear algebra course, you're used to n by n matrices having n eigenvalues, possibly some multiple ones, but if you count them all, you get n. And now this is an infinity by infinity matrix, and you're expecting to see infinitely many eigenvalues, which you did here. I mean, you saw lots of eigenvalues here and here, but not in this example. 0, nothing, no eigenvalues. Well, apparently that can happen. However, the spectrum is not empty. It contains at least the point 0. How do we know that? Well, we will see. What does it mean for 0 to be in the spectrum? Well, you have to show that A minus 0 identity is not invertible. But that's clearly A itself, and why is it not invertible? Well, we discussed this in the very first couple of weeks, probably even the first exercise session. This operator A is not surjective because it's always leaving a 0 here. So vectors that have a non-zero entry in the first component are not in the image of A. So the image of A is not all of LP, it's not surjective, hence not invertible. But it's injective, right? So 0 is not an eigenvalue. In fact, A has no eigenvalues. You can try whatever you want. A minus lambda I is always going to be injective. Strange. Okay, so what have we learned from these examples? The set of eigenvalues can be a nice closed set like this, or it can be something like the open unit disk, or it could even be the empty set, or lots of other things can happen. The spectrum, in contrast, is a bit more well behaved. It always has the following properties, and that's going to be our first little lemma. The spectrum of A is always closed, bounded, and non-empty. So this couldn't happen here, that couldn't happen because it's not closed. This could happen.